Thank you. I would like to thank the organizers for inviting me to give this talk, and this place is certainly an inspiring place to be. So, so this is a joint work with Jan Fedorov and Nick Sim. So we're all from Queen Mary University of London. I'm impressed actually by the organizers who managed to find the official title of my institution, which is Queen Mary in Westfield College. When I joined this institution back in 1996, Queen Mary acquired Westfield College. And then it was legally bonded to have Westfield everywhere. But of course they didn't want to have it, so that in small print somewhere it appears incorporating Westfield College. As of August 2013, Privy Council agreed that we can drop Westfield College, so it's Queen Mary University of London now. Right, so I will start with motivation. And first, if I need to define what this talk is about in one sentence, this would be about extending the Shakshahani result from discrete setting to continuous setting. But on this way we get into fractional Brownian motion and Gaussian unitary ensemble. So the motivations are manifold. So the first one is that we're interested in log correlated random fields and relations to random matrices. And of course, random fields with long dependence appear in many areas of natural sciences, actually social sciences, economics, for example. And in the context of random matrices, there were a couple of talks here in this conference. So, for example, Gaussian free field is a model for fluctuations of height and growth processes. And there is another work, for example, by Virag and Ryder, who showed that the log of characteristic polynomial for Geneva ensemble has fluctuations explained by Gaussian free field. But we are now interested in how are there any situations where these log correlated fields appear in one-dimensional setting. So that's one motivation. Of course, related to it is that one of the formulas that John showed. So this is an example of one-dimensional F1 over F noise, so a process with log correlations. And it appears naturally in the settings when you consider random unitary matrices. So there was this work by Hughes, Keating, and McConnell, where they showed that if you consider this object, then in appropriate functional space, it converges to this object. So that's another of our motivation. We want to understand how one can extend this result from unitary matrices to Gaussian Hermitian matrices. And then we also wanted to find out, so this one is, one can call it a stochastic Fourier series or random Fourier series, and we wanted to find an example of a stochastic Fourier integral. So how we extend this to, how we go from sum to an integral. So these are kind of several motivations for our work, and on this way we encountered relation to fractional Brownian motion. Maybe I should first start with GU analog of the result of Hughes, Keating, and O'Connell. Of course, anyone who knows Johansson's work, who generalized Shakshahani from unitary matrices to Gaussian matrices, what you do is simply replace powers by Chebyshev polynomials, would easily guess the answer. but it's one thing to get the answer, another thing to prove it. So it requires some work. So I just want to outline the structure here, and probably wouldn't say that much about the proofs. So we consider Gaussian unitary ensemble, and just to fix normalization, so this matrix is H, n by n, Hermitian, and the joint probability density function of matrix entries is proportional to exponential n 2n trace h squared. And we also, as you know, have semicircle law, which I don't want to state it formally, but it gives you the density to pi of eigenvalues. So in the limit of infinite matrix dimension, eigenvalues are all distributed on the interval from -1 to 1, and this is the density. Right, to state the result, of course, so this is a strange object. A quick inspection shows that for any fixed x, the series diverges. So you cannot think of it as a just proper function. It is actually a generalized function, and you have to consider it in a space of distributions. And Hughes, Keating, and O'Connell found appropriate space and showed convergence, weak convergence in that functional space. So I just want to show you what is the space for Gaussian unitary ensemble. For that I need to define Sobolev spaces, or sort of Sobolev spaces. So VA. So these are square interval functions. On the interval from -1 to 1 with this measure, dx over square root 1 over x squared, and such that the sum of Chebyshev coefficient squared times 1 minus k squared to power a is finite. So CKF is 2 pi interval -1 to 1 f of x tk x d mu x. So it's just Chebyshev coefficient. So of course Chebyshev series is just Fourier series in disguise. You change variables and you arrive at Fourier series. So it's kind of, we are moving in more or less in parallel with what Hughes, Keating, O'Connell did. Right, so then V minus A is due to VA. It is convenient to kind of choose this dual. Okay, so now the random vector I want to consider is f of x, which is sum over xk divided by square root k tk of x. Xk are independent standard normal variables. So again, for any fixed x, this series diverges with probability 1, so you have to consider it in a functional space of distributions. So f belongs to V minus A for any A greater than 0. Okay, what else? And finally I want to define this object that is kind of straight analog of V sub A. So I define it slightly differently. I use different notations, dn of x, and this is log absolute value of determinant h minus x times I. And then dn tilde is dn minus expectation of dn. So now I'm ready to state the result. So theorem 1, we have that for every a greater than minus 1/2, d tilde nx weakly converges to f of x in V minus A. So weakly convergence means that for any continuous functional, not linear constant, but just continuous functional, we have convergences in the mean. Huh? How? Thank you. So why our proof is slightly different from the one that works for unitary matrices, simply because for unitary matrices you have the nice machinery that was employed by Dekanish and Shahonitz and some nice formulas. We don't have it, so you have to do something to prove it, but it's not such a big deal, so you can prove it. So why I'm showing this result? Because I want to show you some argument how we arrive to consider mesoscopic scales. So that what is the covariance structure of this field f of x? So as usual, we have to consider f on two test functions. So that E f g f. So these are nicely defined objects. You do the calculation and you arrive at this integral operator. So it's one of integral from minus 1 1 minus 1 1 1/2 log 2 x minus y f of x g of y d mu x d mu y. So that's the covariance operator. And you can't escape to notice that Chebyshev polynomials are just eigenfunctions of this integral operator with eigenvalues 1 over k. So there is a structure to this formula. And so if we want to go from sums to integrals, we have to have a continuous spectrum, so to say. And therefore we have to go from this fixed interval minus 1 to 1 to an infinite interval. And of course, if you're on the global scale, you are bounded to minus 1, 1. If you're on a local scale, then it just there are too few eigenvalues. So this mesoscopic scale provides you a good playground where you can actually hope to obtain a continuous analog of this formula. Okay, so that's kind of part of motivation and explanation why we are interested in mesoscopic scale. So now I want to say a few words about fractional Brownian motion, because it does play significant part, or important part, in our considerations. So fractional Brownian motion So this is a Gaussian self-similar process with stationary increments. Right, so this bit self-similar means that if you consider this process under scale time, then as a process it has the same distribution as a to power h bh t. Whereas it means that if I observe this process in any fixed number of times, then we'll have equality in distribution of random variables on the left hand side and random variables on the right hand side. And you all know what this process with stationary increments is. So actually this is quite a strong property, and you can derive quite a lot of properties from that one. So self-similarity plus stationary increments imply that firstly bh at 0 is 0, then the expected value of this process is 0, so this is 0 mean process, and then you can also derive the covariance. And it has a very simple form, which is some constant times t1 to 2 times h plus t2, 2 times h minus t1 minus t2, 2 times h. So you see that indeed this process has very slow correlations. From this you can also infer that the scaling parameter, scaling factor, what is it? H is between 0 and 1. And actually, the extreme case of h equal 1 is trivial. So you have b of t same as t times b of 1. So this is just a straight line with a random slope. And you just obtain it from this formula pretty easily. And then if h is 1/2, then we have standard Brownian motion. Just doing simple calculation, you will see that there is a maximum of t1 and t2 if t1 and t2 are positive. And actually 1/2 is a kind of a critical value, and you can understand why, because if you look at two successive increments, so r s t, so you look at the increment going from time r to time s, and then the increment going from time s to time t, then if h is greater than 1/2, then successive increments have same sign, so which is kind of you go to this extreme case of h1 where just you move across along the straight line. And if h is less than 1/2, then successive increments have opposite sign. So that this process does a lot of zigzagging. The fractional Brownian motion has a continuous path, Gilder continuous path, but they're not differentiable. And actually what is my point here is that the Hausdorff dimension of the graph is 2 minus h. It's kind of known fact. So that in the limit, when h goes to 0, this graph of this path, it fills the unit square densely, so to say. So this is a very interesting limit when h goes to 0. And looking at this formula, you would quickly realize that it's not straightforward to take this limit. It will have to be in some distributional sense again. So instead of going into distribution theory, we employed a different method. We just decided we want to regularize this limit. And for that, I need to recall integral representation for fractional Brownian motion. So it is known, then you can write it as the following integral. 1 square root 2, 0 to infinity 1s 1/2 plus h, and then you have exponential minus its minus 1 over 2 dbs plus complex conjugate, where bs is just complex version of standard Brownian motion. Two independent copies. So then a very natural way to regularize is to write here minus as. So this will be regularized version. Again, you can obtain all the properties of regularized fractional Brownian motion from this integral representation. So for example, BAH 0, 0, mean value is also 0, and then the covariance structure is given by formula by FF. BH 81 BAH T2 is have the same structure, although the function is slightly different. So this allows you, it's a Gaussian process as well. So everything is defined by the covariance function. So this expression allows you to take limits. So for example, if you take the limit a to 0, you will recover fractional Brownian motion. And if you take the limit h goes to 0, now you can do it. You recover or you define a regularized version of fractional Brownian motion with Hurst index 0. So phi 0a is simply 1 quarter log t squared plus 4a squared. And you see that our friend log appears here. Okay, so now I can define regularized fractional Brownian motion with Hurst index 0. It is just Gaussian process with mean 0 and covariance given by function phi a 0. And of course we also have a convenient integral representation for it. Okay, so that's all I wanted to say about fractional Brownian motion. Now mesoscopic scale on Gaussian random matrices. So let us fix a reference point, x sub naught, inside the spectrum, and introduce a new variable, x, which is x naught plus tau divided by d sub n. And the scaling parameter d will define my scaling regimes. So that in the global regime, the ones that I already addressed when generalizing Hughes-Keating-O'Connell theorem to Gaussian unitary matrices, Dn is 1. And in this regime, in the unit t interval, you have macroscopically many eigenvalues of matrices. And then you have local regime. This is when Dn is n. And in this regime, the number of eigenvalues on average in a typical interval of length 1 on tau's axis is finite. And then anything is between is a mesoscopic regime. So in this regime, if I look at t interval of length 1, I will have many eigenvalues of random matrices, but not proportional to matrix size, but there will be infinitely many of them. So it's Dn goes to infinity, but Dn divided by n goes to 0. So this is kind of most general definition, and we stick with a particular case of mesoscopic scale given by this condition that d sub n is n to power alpha, where alpha is between 1 and 0. So this is not optimal, and I think that our results can be extended for kind of when you get closer to the local scale. But at the moment I don't want to make statement. I think that we can do n divided by log n. But to be on the safe side, this will do for now. Okay, now I can state our main theorem. So define this linear eigenvalue statistics. As I said, I don't want to work in functional spaces, and we prefer to work with regularized quantities. So therefore, in this mesoscopic scale, we want to go slightly away from the real axis to avoid singularities. Right, so correspondingly, I define my statistics as this one, minus log, then det h minus x naught plus tau plus. Right, so what we do? So this is x scale, so we take point x naught and we consider a small neighborhood of this point slightly off the real axis, and this is a stochastic process where tau for large n varies between minus infinity and plus infinity. So this is our quantity of interest. And then we consider the centered version of this process. So eta is a fixed parameter which regularizes our statistics. Tau is a running variable, and n is the size of matrix. So here is this theorem. For every alpha between 0 and 1, this random process or sequence of random processes converges in distribution, and I will say what I mean in a few moments, to a regularized version of fractional Brownian motion with Hurst index 0. And then convergent distribution means that if I take any fixed number of times, then I will have a vector, and this vector converges to similar vector composed of samples of fractional Brownian motion at those times. Okay, so this is a point convergent theorem, but we can also state, or we can also prove a functional convergent theorem. Not in the generality that we wanted, but still it is something. So we also have functional So I want to consider this process on a finite interval. So unfortunately we can't do tails. Right? So if a is greater than minus than infinity plus infinity, then V eta n tau converges tilde converges weakly to regularized version of fractional Brownian motion in L2 AB. So if you kind of consider, if you smooth this process on with any square interval function, you will get convergence on finite interval. Going to plus and minus infinity requires some tightness conditions which at the moment we are unable to verify. Proves to be difficult for some reason. Okay, so that's the connection or relation between Gaussian unitary ensemble and fractional Brownian motion. And now I want to talk about extending Diaconis-Shahshahani to continuous setting. Now, this will be random Fourier integral. To show this connection, I want to show you a formula which one can derive using some fairly straightforward manipulations, I would say, but it is not entirely obvious at the first sight, I admit it. So if I look at this linear eigenvalue statistics, I can write it as an integral. This will be integral from 0 to infinity ds over square root s exponential minus eta times s, and then dn s plus complex conjugate, where bns is again 1 over square root s sum j from 1 to n exponential minus s dn x naught minus x sub j. X sub j are eigenvalues of matrix GU matrix H. Oh, this is 1 over square root s trace exponential minus s dn h minus x naught I, maybe plus. So this is pretty similar to those formulas that John wrote and unfortunately wiped out from the board. Instead instead of powers we have these objects. Okay, so if you now you might remember a similar formula as I wrote for fractional Brownian motion, a regularized fractional Brownian motion with Hurst index 1, except that here we had white noise. Right, so our last result is that these statistics indeed converge to white noise in the limit when n goes to infinity. So theorem 3. Of course, white noise is a generalized stochastic process, so I have to define what distributions or what test functions are in my case, and our choice of course, we have a singularity near s equals 0, and we want to avoid getting close to the 0. So choice of test function is this. So this is just smooth functions with compact support on half line. Then for every alpha 0, 1, we have the statements. So firstly, the expectation of B smoothed with function xi is small, so it goes to 0 as 1 over dn. Then B, we can also say something about the covariance function. So in the limit n goes to infinity, expected value of 0 to infinity xi s b n s ds xi1 xi2 is simply integral 0 to infinity xi1 xi2 ds. So we have first moment, second moment, and now the distribution. We can actually calculate the characteristic function of this that integral. So expectation of exponential real part. So indeed, we have convergence to white noise. So because of that, we consider this as a continuous analog of Diaconi-Shakshakani formula. So that's our main point in this work. I don't have time to go through details of proofs, and they are gruesome details. I think that our first when we started thinking about this problem, we kind of wanted to use the standard techniques in Gaussian unitary ensemble. So you have the kernel, you want to find mesoscopic correction to the front kernel, and then you just try to go from there. To our surprise, we found that mesoscopic corrections are not known. I don't know, maybe Laszlo will say something about it, but to the best of my knowledge, I don't know mesoscopic corrections to the same kernel. And the only case where those corrections are known are circular unitary ensembles. It's unitary matrices. This is done by Sochnikov some 10 years ago or so. And then, of course, I should say that even if you know mesoscopic corrections, it's not a straightforward way to just prove everything. So we settled down on Riemann-Hilbert problem, and it was pretty effective. We benefited from Igor Krasovsky being nearby, so we just catch a tube and talk to him. And he published a paper where he studied correlations of characteristic polynomials of Gaussian unitary matrices on the global scale using Riemann-Hilbert problem. And in that approach, what you end up, you do your Riemann-Hilbert not on the Gaussian weight, but on the modified Gaussian weight, which comes from those characteristic polynomials. So you have Gaussian exponent times x minus xj to power alpha. And it appeared that it is possible to almost repeat his calculations with some modifications for our case, where we go slightly into the complex plane, but then equally we work on the mesoscopic scale. And that gives answer. So, and then this theorem, again, it just we rely again on Riemann-Hilbert problem. It wouldn't be interesting to know. It seems to be quite a heavy machinery for such a simple case as Gaussian unitary ensemble, but this is as best as we can do for the moment. Now, open problems. Okay, this is a very specific ensemble, and we believe that this result is probably more universal than just so I think it would be possible to extend it to invariant ensembles with convex potentials. That should be possible, and I don't know, perhaps it is also possible to extend it to Wigner matrices, that at least GNA has some ideas how to do it. But for example, for Gaussian orthogonal ensemble, we are stuck, we don't know how to do it, because we rely so heavily. It's actually every calculation in our work uses quite a lot from what is known about Gaussian unitary ensemble. So this is quite a challenging problem, how to generalize what we did to real symmetric matrices, for example. That's all I wanted to say. Thank you for your attention.